Took this doubling every year and extrapolated it 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Good afternoon. Since the beginning of the class, we have been talking about, well, the most, I would say, like the boring part, like how to interact with your processors through the instruction set architecture. And then we start to know that, well, being a programmer, you have huge influence on the application performance running on a von Neumann machine. So today we are going to start another topic, and we are going to talk about this topic all the way through the midterm. That is how to design a processor core and how do you utilize the features, or say, like, given that you know the processor is designed in this way, how to better utilize the underlying processor to make your software faster. So that's the whole goal of computer architecture, is that knowing the hardware, you can make your software faster. So, sometimes people like to change. And if I didn't say anything, you probably would expect that I would start with another slide on von Neumann architecture. But let's have a different way to start the lecture today. So let's start by a reading quiz today, a pop-up quiz today. So right now, let's start thinking about this question, and you are given 90 seconds to tell me what do you think about. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now I want you guys to discuss in small group and tell me, well, so before that, I think I should send out the code first. So let me do that. Okay, so I have sent out the question now. So it's a good time for you guys to open that question, and then right now let's go into group discussion. Wait. What's going on? Oh boy. Group discussion. Wait. Group discussion. Group discussion. Well, looks like there are some technical issues of Zoom on Zoom group discussion this time. Let me try this again. Doesn't allow me to finish. Group discussion. Okay, all of them finish within 3, 2, 1. Okay. Okay, so let's go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now looks like after discussion, a majority of you think it's B. Can I have some of you telling me like what your group is about? Okay, Harris, you just raised your hand. Okay, what do you think?
So originally our group was divided between the two because on one hand, A has one less assembly instruction, but on the other hand, B, the multiply instruction is significantly higher in CPI. At least that's the assumption.
Okay.
So eventually we decided to go with B.
Okay, so that's the that's what you got, right? So let's see, like, okay, really in modern processor architecture, right? So I have this arithmetics 2.c, and it implements the multiplication and as well as the shift minus, right? So given that you learn CSE30, I don't think I need to argue with you. I don't think we need to explain why these two are equivalent, right? So now let's try to compile the program and run it on my machine, right? So let's see, right? So the first timer will be the multiplication, and the second timer will be the shift and minus. What did you see? Which one is faster, A or B? Multiplication is faster or shift is faster?
They're actually within 10% of one another.
They are actually within 10%, right? And in fact, if you run it multiple times, right, you will figure out that using multiplication is consistently faster, right? But you said one thing right. The CPI if you just look at one instruction, the CPI of multiplication on the processor that I'm having on my laptop is actually an Intel Core i7 processor. It's actually longer. So why this is the case? So and so the thing is that, well, you guys learned a lot in the past saying that, well, you should use like a lot of exotic flavors of programming technique, like use a lot of, optimization, shift, or whatever to replace the regular multiplication. But this example just told you what? It's in modern processor architecture, in the real world applications, they are not actually that faster as you can imagine, and sometimes they are slower. So right now, so in this, starting from this lecture, I'm going to tell you why those, I call this like grandfather old optimization techniques, why they don't work anymore. Right, so that's the purpose of the lecture today. And thanks for your for your feedback, because that's actually what I expected to hear from you, because that's what every professor in CSE30 will probably teach you about. And that's what CSE140 is going to tell you about, like implementing ALU in multiplication is a lot slower than doing that with shift, right? Because for shift, it's probably just a mux and you can do it, right? But for multiplication, you definitely have to go through multiple times. So from what you have learned in the past, you don't think there's any chance the left-hand side, the version A, can outperform B. But through the demo we just showed you, version A, the multiplication version, is consistently faster than the right-hand side. Why? So that's the following lecture is going to be about. Okay, so today we are going to talk about first single cycle processor, and then we are going to talk about a concept of pipelining and how to design a 5-stage MIPS pipeline processor. And it's a best chance for you to have an idea about what's going on so if you have that big picture of 5-stage MIPS pipeline, it will make your life in the lab a lot easier. And finally, we are going to talk about pipeline hazard. All right. So we didn't specifically talk about von Neumann architecture today because we have this slide. So we have learned that right now, like in processor, we use the instruction set architecture to talk to the external world, and every program encoded their desired operations in instructions. So to have your program running or say everything about performance is regarding to how your processor is going to execute an instruction. So this slide gives you the life of a dynamic instruction. So dynamic instruction means that an instruction that is currently in execution. So the instruction, first of all, right, we have to fetch the instruction pointed by the PC from memory. And then this stage is called instruction fetch. So we fetch the instruction from the instruction memory at the location pointed by your PC. So PC, program counter, we give it a different name, but it's actually the memory address of an instruction. So if you are currently doing lab 2, the PC is actually the input of instruction memory, because the PC is nothing else than the memory address of your instruction. And after get that instruction from your memory, the processor will have to decode instructions to figure out what's the desired operation and the operands that the instruction, the operation depends on. So you have to prepare the source value that are already in the registers and make them the input of the next step, which is the execution of those instructions. So depending on what instructions you have, If it's a regular ALU instruction, then the instruction would just use those register value to perform arithmetic logical operations. If it's a conditional branch, the ALU will perform a comparison on register value to determine if we have to change the next PC. So it depends. So the branch outcome is usually equal or not equal. And if the instruction outcome tells us that you should change your PC, we say the branch is taken. Otherwise, if your next PC is still PC plus 4, then we say it's branch not taken. And finally, if it's a memory instruction, we still do ALU computation, but this result will be the effective memory address to access your data memory. So your data memory will use the ALU outcome to perform access, and depending on this is a load or a store, we will perform read or write accordingly. And finally, there's a write back stage will present your ALU result or read value in the target register. Because we want to proceed, so don't forget, we also have to update the PC. And if the branch is taken, we have to set the branch target to the branch target address. And otherwise, we just advance to the next instruction. So this slide just gives you an overview of what a processor should do during the execution of a program. So given this knowledge, the most simple and naive implementation, which is exactly what you are doing in lab 2, lab 3, throughout lab 4, is trying to implement is single cycle processor. So the basic idea of single cycle processor is that we put those data path elements and control signals within a circuit, and everything that you see in this slide, they have to finish their work within just one cycle time. And if you want to dig into the detail of this single cycle processor design and map it to the tasks or say the life of an instruction that we just mentioned, so you can basically figure out that this part of a circuit is performing instruction fetch in a way that you can see we have a PC that fit into as instruction memory as the address, and the instruction memory will output 32-bit values. And then afterwards, after receiving that, the decode stage will be separated into two parts. Taking the most significant six bits from your instruction, that will be fit into the control unit, which will set up those control signals to all the ALUs that we have in the processor to make sure that they will function appropriately during the execution of the instruction. And the rest of the bits will be used as the following. If it's an R-type, well, no matter what type instruction is, the 25th to 21 bits will be used as the first register read input, and then the second the next 5 bits of it will be used as the second read register input. And the target of updating your value, depending on what kind of instruction you are, if it's R-type instruction is the third register, if it's the I-type instruction is the second register. So that's why we have a mux here to choose. And which value to choose is depending on the control signal that's sent out from the control unit. And the control unit would be able to tell if this is an R-type or I-type from the opcode of the instruction. And finally, we also have immediate field that will be extended from 16-bit to 32-bit. And the last 5 bits, 6 bits, also will be used as the supplementary LU code for arithmetic instruction to know like what's the corresponding LU operation. So after decode, it's a time for execute. And after execution, depending on what instruction is, we will use data memory to access, or we just bypass it and feed it to the write back logic, which would present your result in the target register. And to update the PC, there are two parts of the circuit. This is the 4 through 1. If there's no branch or the branch is not taken, we are going to use PC plus 4. If there is branch, then we will use the LU output and as well as a control signal saying that this is a branch to set up the mux and select from the offset of the current PC. So that's the design of a single cycle processor. So given that we have detailed explanation on single cycle processor, there are a few things I want to ask you about. So why don't you spend 90 seconds to go through this question and thinking about how many of this is correct, are correct. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so well, looks like there is the result is very diverse. So why don't you guys have a discussion within your small group and let's see what's going on. Let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like now more of you choose D, but there are still significant of you think it's C. But at least you guys agree that two of them, well, at least one of them are correct because like no one chose A, right? So can some of you summarize the discussion in your group and why that leads to your decision now? So I have Byron. Okay, you are the king. I also have Harris. Okay, I will also keep you.
Hey.
Okay, so you guys can have a discussion session here.
Oh boy. Okay, so.
All right.
Well, let's start off with the basics. My group did 2.
Okay, so Byron, how about your group?
Our group was debating between 3 and 4.
Okay.
So
So
see, that's why we want to discuss. Okay,
right.
Go ahead.
I guess I'll start. So the ones we were going for was if a single cycle implements MIPS ISA, then the memory's instruction will determine the cycle time and hardware elements. All right, now why is that? Well, the idea here is that depending on certain instructions, you may have to load more data into registers, or you may have to execute further instructions. So for example, a write, like writing into data would incorporate more, what is it? It would incorporate another cycle of accessing memory than say an addition between 2 registers.
Yeah,
Okay,
but we're doing a single cycle processor. So basically it's just going to be the long, that's going to be the, as long as it takes to get it done. That's how long a cycle is determined.
Okay, so I think there's a confusion here about what do we mean by cycle time? Do we mean clock cycle or do we mean like?
So the cycle time, right? What's the clock? What's the cycle time? It's the clock cycle time, right?
Mm-hmm.
Right, and this definition should be very clear, right? And if you are confused about that, I think the person should be blamed is probably your CSE140 instructor, right? So the cycle time is we set for the single cycle processor, right? We accomplish all tasks within a cycle, right? So the clock cycle time means that the time we need to finish, we need to go through like everything we mentioned here, right? So if you want, so from the beginning to the end till the end, that produce the final result, because your cycle time must be long enough to accomplish all of those, right? So the only type of instruction that would go through everything is actually the memory instruction, especially specifically the low word instruction, right? So the time to get results from your memory would determine your cycle time. Okay, Anwar, question?
Just out of curiosity, so is this related to why like CISC architectures might underperform relative to RISC in that they take longer if there's a like worst case, a really complicated instruction that causes a difference in timing?
That was true before 95.
Okay.
That was true before 95. And that's actually, I show you guys the demo. So the demo that I just showed you in the very beginning, right? Your answers, well, I remember more than 80% of you chose B, right? Your answer is correct if you are using a processor from back to the 95. But it's not true anymore, right? So that's why I try to de-emphasize the importance of instruction set architecture in CSE141. But that's a good question to talk about, right? But okay, but here I think both of you would agree that the memory instruction would determine the cycle time, right?
Mm-hmm.
Okay, so let's continue. Okay, so this you all agree. How about the third one?
Well,
So
without pipelining, I would say that that's the case. If we have pipelining, then that's a different story.
But why without pipelining? And actually, we are not having pipelining right now, right?
Right.
And what's the story now?
Well, without pipelining, you're going to have certain segments that are not doing any work, while some
So
segments
thinking
are.
about like the latency, the latency of a processor, right? Like is so long, right? But most of the time you are only using part of it, right? Okay. So how about the force?
So in this case, we weren't exactly sure because of the wording. Like when you say always
Why?
reduce
Okay.
cycle time,
So the wording, there's no issue with the wording.
okay.
So why that wording make you
Well,
not 100% for sure?
because it depends on the instruction that you're removing, right? So because the cycle time is determined
Right.
by the longest
Right.
instruction,
So if today I say that my processor doesn't want to support, let's say like shift instruction, does that affect your cycle time?
no.
Not at all, right? So this one is wrong. Okay, so how about the first one?
Professor, I'm sorry to mention this again, and feel free to blame our CSE 140 professors for this. But again, what is the difference between a cycle and a clock cycle? Because when we say
it's the same.
Okay, but then if that's the case, how
the cycle time is the time you need to finish a clock cycle.
But wouldn't the memory instruction be independent of?
So this is single cycle processor, and did you see? Did you? And
Yeah.
and like if you look at the and as what I said, right? The
Yes.
definition of a single cycle processor is that we get everything done within a cycle. Everything here within a cycle. That's single cycle processor.
Okay. Oh, so the maximum time would be.
Right. So that's why memory instruction determines your cycle time, right?
Oh, okay. Because there can be instructions that are less than a cycle in that case.
Yes. It can have some, you can have some lag. There's some slack, I guess, for instructions that aren't as intensive.
Right.
Okay, so none of you mentioned the first. What do you think about that? Correct or not?
By definition, right?
Yeah, so the thing is that by definition, the CPI of a single cycle processor is always 1 because this is a single cycle processor. No matter it's a multiplication, no matter it's a shift, no matter it's a load or a store, everything is always 1, right? So for this question, right, the only thing that is not correct, and thanks both of you, I think this is very good discussion, right, and help your classmates to understand. So the only thing that is not correct here is 4. So the answer should be D for this question. So I just put it wrong, right? So the answer should be D because this is correct, this is correct, this is correct. All right. So all right. So now that if you have a single cycle processor, let's compare the performance of these two versions of code again. All right, that's right. 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so I think we still need a group discussion for this question. So why don't you guys go ahead and just have a 1-minute discussion? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so from what I learned from you, so this time 68% of you think it's C. So can I have some of you share what your group is thinking about and why do you advocate for that answer? So I have Japan.
So given they are both on the same single cycle processor, they have same number of lines, and I would assume they have same dynamic instructions. They're supposed to be around. They have the same CPI and same instruction, same frequency. They are that's supposed to be the same.
Okay, so good answer, right? So don't forget, for single cycle processor, the definition, by definition for a single cycle processor, each instruction take exactly 1 cycle to execute, no matter, as I just said, right? No matter it's a shift or it's an MUL, right? It sounds like, well, a lot of you spend a lot of time thinking about like, well, you know, like for MUL instruction, it takes longer, right? So, but the truth is that for a single cycle processor, it's just everything must be done. No, every instruction must be done within a cycle, and the cycle time is decided by the longest instruction. So even though we can finish shift very, very quick, you still have to wait until, or you still have to wait until the cycle time arrives, right? So that's why we said most of the time in a single cycle processor, your hardware units is idle, because for this case, shift takes really quick to finish, but MUL takes really long time. But it's all about the same cycle time, the same clock cycle time. So if they have the same instruction count, right? Every parameter is the same in their performance equation. Okay, so Harry's question.
Well, my question was going to be, why is it the case that it's not possible to essentially short circuit certain instructions? Like if shift.
Well, if you, okay, good question. So that kind of processor is a different type of processor called multi-cycle processor. And you can find this kind of processor in the appendix of the textbook. And what you are saying is exactly correct. You can do that, but it's a different type of processor than a single cycle design.
Okay.
Okay. All right. So in single cycle processor, both version runs about the same, right? So you can see like, okay, in the past you learned from CSE30 that you should use instruction with faster hardware implementation, but it doesn't work for the case in single cycle processor. So, some of you mentioned that we can short circuit that, and that's actually the majority of processor type in before 1995. That's called multi-cycle processor, but the textbook already kicked it out because you cannot even find a multi-cycle processor implementation right now. So what's the mainstream of processor design nowadays is the pipeline processor. So the pipeline processor, the basic idea of pipelining is like this. So if you want, so not sure how many of you remember this. So this is the photo that I just took last weekend in UC San Diego campus, and you can see like both Dr. Seuss and the cat is wearing a surgical mask. So it must be this year. Otherwise, usually they won't do that, right? So on UCSD campus, there are many places that you can find pipelining. And what I really want to say, like if you are new to UC San Diego, you probably never visit this, right? But if you have been in UC San Diego for years, you know, like Subway, right? So for Subway, it's a good example of pipelining in a way that, it has the fashion of pipelining, and we will talk about this later. So the basic idea of pipelining is that, instead of having all components within a processor to serve just one instruction, we have different parts of the processor works on different instructions simultaneously. And the clock signal controls and synchronizes the beginning and at the end of each part of the work. And a pipeline register between different parts of the processor will keep intermediate results necessary for the upcoming work. So that's why I'm saying this has some analogy of Subway. So thinking about many shops, there's probably just one people serving you. So even though the shop has a lot of facilities like the register, like the food trays, or like coffee cans, right? So whenever you order, right, no matter what you order, that person would go grab the stuff you want and finally put your order in a register and get money from you. And before the person finish your order, there's nothing else we can do. He can do, right, or she can do, right? But think about pipelining or say Subway. It's a different model. So first of all, when you step into the line, you go to the first person. Usually he will ask you or she will ask you like what kind of bread, right? Like for me, I usually pick like flat bread. And do you want what kind of meat do you want, right? And do you want to toast it, right? So that's the first stage, right? And it's basically like an instruction fetch in a certain way, all right? Like what kind of sandwich you want, right? So that's the very first stage. And after he or she put it into the oven, right? That's like a register or something. Then the second person would take your bread from the oven and ask you about like, okay, what are the rest stuff that you need, right? So that the rest of the stuff is kept in your mind. That's actually like a pipeline register as well as the oven, right? So after you are done, like, okay, cucumber, lettuce, tomato, those are the stuff that I like the most, right? And then your stuff will be forwarded to the register, and the register will ask you like, okay, do you want to add chips or soda, right? And then you're done. But in the meantime, the first and the second person that you interacted with, they are serving different customers at that time. So pipeline has that kind of flavor in a way that, well, first of all, it's controlled by a clock. So this is a clock. We divided your circuit using pipeline registers are those that we colored in yellow. And all the pipeline registers, as well as the very, very beginning of your circuits, they are controlled by the clock. And whenever the first clock signal comes, the first job will come in. And then the second clock signal comes in, the first job will advance to the second stage in the pipeline, and another job can use the free up resource from the first instruction, which to occupy the first part. And when the next clock cycle comes in, the red job will move to the next stage, and the orange can move to the second, and it frees up the first part of the circuit for the new job. And whenever the new jobs come in, we will keep advancing your task until we finish that. So that's the concept of pipelining. So that's the concept of pipelining, right? So if we map this concept to instruction execution, you can imagine we divide the job of an instruction into different pieces. So when the first instruction enter in the first cycle, we will do the first pieces of the task. And then for the second cycle, the first instruction would advance to the second, and the first part of a circuit will be yielded to another instruction. And then if you keep going, if we assume that the job can be finished within 5 different stages, or say 5 different cycles, then after 5 cycles, you are going to see the outcome from instruction 1, and then you are going to have the 6th instruction coming in. So if you keep going, you will find quite a few things from here. So first of all, after a certain point, the processor is actually finishing an instruction as each cycle. It's actually finished an instruction for each cycle. So what does that mean is that if we can finish 1 instruction per cycle, then it tells you that the average CPI of this pipeline processor is also 1. And another thing is that your hardware units are all in use at this point. So in this way, a perfect pipelining would maintain the same CPI as a single cycle processor, but keep all your hardware parts busy. So that's the good thing about pipelining. But where the real pipeline performance gain coming from? So that's why I want you to use this question to evaluate if I can pipeline a processor, by what degree is faster and why is this fast? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, I already sent out the question throughout the chat. So open it right now because we are going to do group discussion. But before you do this group discussion, I just want to let you know why we need a group discussion, because A, B, C, they are both answers that a lot of people advocate. So looks like we definitely need you guys to discuss in carefully, right? So that's, go ahead and do it now. All right, so let's wrap up just put your answer in as soon as you can. We are going to wrap up the discussion in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so, well, most of you think it's C still because you think, well, the most popular answer, well, although it's just slightly popular, it should be right. Or most of the time, because it's normal distribution, so you think the professor always likes C as the answer. If that's the way how you think about the multiple choice question, you probably will miss a lot in midterm. All right, so can I have some of you telling me like what your group is talking about? Like, what do you guys think? Okay, so Byron.
So there was an equation in the textbook that said that the maximum speed up is the latency, or is the I guess latency of the non-pipeline version over the number of stages.
Yeah, but okay, but given the evidence, or say the stuff that we have in this processor, right? Does that apply?
No, because they're different. The stages are different times.
Right, right. So what does that mean? So how do you get the answer?
Well, if say it was ideal, then it would be 4 for the maximum speed up.
Oh, how
And maybe
come?
because it's less than ideal, we would go less than that.
Okay, how come?
Because it is.
Okay, so tell me one thing, right? Okay, so first of all, I didn't pay attention to what the textbook is wrote, and sometimes, you know, like their sentences are misleading. So but you know, like, okay, first of all, when we talk about speed up, right? What's the definition of speed up?
The execution time of x over y.
The execution time of x over y, right? But for this case, who should be on the top? Who should be on the bottom?
The top should be the original, the non-pipeline.
Okay, so
version.
that's a like single cycle, right? Single cycle and pipeline, right? Okay, so what's the execution time of a single cycle over pipeline?
Well, we know that the single cycle is 20 nanoseconds. Sorry.
Yeah, no. So what's the equation looks like?
The equation. Sorry, it's IC times 1 times was it 10?
Cycle time, right? And the cycle time which I put here is already 10 nanoseconds,
okay.
Right? Yeah. And the IC here, you say the CPI is 1 for a single cycle processor, right? How about pipeline processor?
It would be 3. Or sorry, not
Why?
3. Sorry, what am I saying? Sorry. I don't know. Would it be 5 because it's 5 stages?
No, look at the slide, right? Right.
Oh, it's also 1.
Boy.
Oh yeah.
Yeah, remember that after some point, it's going to be 1, right? Okay. Okay. So this is also going to be 1, and ICs are the same, right? So this is the same. So what determines your performance?
The clock, or the cycle time.
The cycle time, right? So in pipeline, in non-pipeline processor or in single cycle processor, the cycle time is the latency that we need to go through everything, right? And for this question, it's going to be 10 nanoseconds. But for pipeline processor, who decides the cycle time of the
longest stage?
processor?
So in this case, 3 nanoseconds.
The longest stage, right? So this one, the longest stage is 3 nanoseconds. So what's the cycle time we should put here?
3 nanoseconds.
Okay, then what's the answer now?
A, 3.33. 10 over 3.
Right. So thanks. Right. So here, right, look at this, right? So computer architecture is not really a class that requires you to memorize a lot of formula. All you need to know is execution time, right? So if you know how the execution time comes from, then and if you know the concept of the cycle time of a pipeline processor is the longest possible delay between two pipeline registers, right? Then the cycle time is not too hard for you to figure out for this question, right? And there are more notes that I have here regarding the cycle time of the pipeline processor, like because your cycle time must be long enough to signal for the signal to traverse along the critical path, but it's also true for a single cycle processor. And during each cycle, the test that you have to do is just try to propagate your result from a pipeline register through a set of combinational logic to another pipeline register, right? So that's why the critical stage would determine your cycle time. And if I say like I want to cut a stage into two, but it's not a critical stage, then it doesn't help your cycle time. And as some of you mentioned, you did pay attention to the textbook, but maybe you didn't, or say maybe the textbook didn't explain that carefully, is that if you want to achieve the maximum speed up, which is equal to the number of stages you have for the pipeline, they must be all the same. Otherwise, it will create a case like this, because this time and usually it's really this case that you cannot make your all possible pipeline stages equally. So the speed up will be determined by the resulting cycle time that is also determined by the longest stage in your pipeline processor. So it turns out it's very limited in a way that it's only 3.33. So for this question, only 21% of you get it right, even after discussion. So that's why really make sure that you pay attention to this question because I think we need more work on getting the concept right. So maybe pipeline is a new concept for you. So that's so why don't we just spend one more question to figure out the concept of pipeline and before we can proceed. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now, well, why don't you guys go ahead and do a group discussion? And well, just give you a hint. The most popular answer is C, but your C, like when you select two, your two might not be other people's two. And I can definitely tell you one thing, that the answer of this question is not C. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after seeing your answers, I'm very, very sad. The reason is because there are still 30% of you think I'm lying because I already told you the answer is not C, right? So I definitely need some of you to share your thoughts and why some of you are thinking that I'm lying, right? So can I have some of you raise your hand? Otherwise, I will pick someone from the group. Okay, so let me see. Our biggest discussion room is actually Warren College. So let's see what Warren College is talking about. So, okay, can I have Yiting Wang? Can you share your thoughts? Hello, are you wrong? Are you wrong? Hello. Hi, what does your group think?
Our group thinks the last answer.
The last answer, you think everything is correct?
Yeah.
Well, but only 6% of your, well, your group has more than 10 people, but there's only 2 of you think it's E. Okay, so you think everything is correct. Okay. Okay. What else? Other thoughts? Okay, so I have Byron. Oh, you are my superstar.
We thought it was D.
You thought it was D. Okay, so you thought one thing is incorrect. What's that one thing?
We think it's the latency.
The latency.
Yes.
Okay, so you don't think this is correct.
Mm.
Okay, so let me go through this one, right? So for this question, right, how much time would it take to execute an instruction in single cycle processor?
10 nanoseconds or 1 clock second.
Okay, how much time would it take to execute an instruction in a pipeline processor?
Oh, slightly more.
Slightly?
Because, well, yeah, I guess if we made each stage 3 nanoseconds, then it would be like 15 nanoseconds.
Right, so it's actually 1.5 times more.
Okay.
Right, that's the latency, right? Okay, so Harris, do you have some other words to share?
My group was under the consensus of it being the answer being D, but our issue was with statement 1. You can always divide stages into shorter stages with latches.
Right, so sometimes like always is so strong, right?
Right.
So if that's something always, it's so easy for you to think if there's an opposite example, right? It's counter example, right? So what's the counter example here?
Well, that's the thing we argued a lot about. We really didn't know.
Well, so look at this slide, right?
Mm-hmm.
If I divide this stage with latches, well, that improves the performance of the processor.
What? No.
Right.
Like maybe if you divided the MEM stage, but if you divide anything else, then it's still going to be dependent on the longest.
So you can always divide stages, make it shorter to improve performance. You can make it shorter, but doesn't improve performance. Did you see what's wrong here?
Correct.
Yep.
Right, so you can divide stages with latches to improve performance only if that stage is a critical path. Plus, you have to consider there are pipeline register overhead that you have to add. All right. So It may not be shorter if the stage is already shorter than the pipeline stage for the pipeline register, right? So the first statement is from both perspectives, like from the hardware perspective, from the overall perspective, they may not be right. But but the rest of them are correct. Okay, thanks Byron and Harris. You guys give us very good insights about this, right? So so again, right? So that's why in the last lecture, at the end of the very last lecture, the last slides of the last lecture, I talk about the latency and the throughput difference. Throughput is like, okay, if I have 1,000 instructions, then the total time to finish this 1,000 instructions is definitely faster in pipeline, right? So look at the pipeline processor design, right? So for throughput, we are looking at how much time it takes for us to finish the whole thing, right? So in pipeline processor, it takes more cycles. So it actually would take a total of 15 cycles to finish this 11 instructions. However, because your cycle time can potentially like, let's say like 3 times faster, right? So 15 times like 1/3 is actually probably equivalent to just 5 cycles in a single cycle design. But for single cycle processor, this would definitely take like 11 cycles, right? But if you just look at the latency of just one instruction, right, it actually takes 5 cycles, and this 5 cycles is longer than a cycle of the single cycle processor. So that's a big difference. So that's the difference by latency and the throughput. So latency means that one thing, just look at the one thing, that's latency. The throughput is that the end-to-end latency of the whole thing, that's the throughput, right? So those are different, right? So that's a different definition between latency and throughput that you have to be especially careful about of the definition of them and the wording of them, right? So the answer to this question is that only why am I always get this wrong? Oh, 3 of them are correct, right? 3 of them are correct. So only one of this is incorrect. All right. So again, right, if you go to this slide, making sure that you know the difference between throughput and latency. All right. So right now, let's talk about the MIPS bi-stage pipeline design. So we now know the concept of of the pipeline design is that we put pipeline registers into the original design and use those pipeline registers to buffer your intermediate result and progress making like advanced instructions based on cycle time, right? So that's based on the clock cycles, right? So that's the basic concept of a pipeline. Right, so and to pipeline the original design is actually not that hard, right? So for this single cycle processor, right, look at that, right? Here's the pipeline design, here's the single cycle design, here's the pipeline design, here's the single cycle design, here's the pipeline design, here's the single cycle design, right? Look at that, right? Except for the title is changing, right? We add more pipeline registers, and also because right now your write back is taking result from the 5th stage, so here we have to keep your write register all the way through pipeline registers and get the result from the 5th stage. Other than that, everything we just keep all the unused parts or the parts that will be necessary for the rest of the instruction execution in the pipeline registers, and we are done. So thinking about that's why we have lab 1 through lab 4 on single cycle processor, but only lab 5 for pipeline processor, because conceptually pipeline processor is very simple to implement and very, very neat. So right now, let's try to run instruction sequence on this pipeline processor and see what's going on, right? So look at this. So right now, like I have the red instruction, which is the add instruction coming in. So it's going to be in the first pipeline stage, right? And the next cycle time, the red instruction will go to the 2nd stage. The orange instruction would be in the first stage. And if you keep advancing, the first would go to the LU stage or say the execution stage. And the second instruction would go to instruction decode stage. And the first instruction will be fetching its own new instruction, right? And then the next cycle, your arithmetic instruction is going into the memory stage, although it's not actually accessing the memory. And there's a reason why we have to do that, which we will explain in a later lecture. And finally, in the fifth cycle, you can see like all 5 instructions, they are in different stage of the pipeline. And for this pipeline processor, the first stage is called instruction fetch, and the second stage is called instruction decode, and the third stage is called execution, and the fourth stage is called memory, and the last stage is called write back. So that's the name of each stage. And as you can see, the pipeline register between different stage is named as the previous stage / the later stage. So that's a pipeline processor design. And see this animation, right? See this coloring, right? So like you cannot imagine how much time I spent on this. So I want to play it multiple times, so you will figure out that, well, the instruction is making progress, right? And how they advance, right? So this is so pay attention to this. Sometimes I think that Disney should hire me because I really make like good graphs in class, right? So right now, you might have a question like, okay, am I going to ask you draw things like that in your midterm, in your homework? The answer is not. We are going to let you draw a pipeline diagram. So the basic idea of pipeline diagram is that each instruction will go through 5 stages of the processor. And this 5 stages, as I mentioned, their names are IF, ID, EXE, MEM, WB in order. And the guideline of advancing instruction is this. An instruction can go to the next pipeline stage only if, in the next cycle, only if no other instruction is occupying the next stage. This instruction can have completed its own work in the current stage. The next stage has all its input ready and it can retrieve those inputs. And fetch an instruction only if we know the next PC, we can predict the next PC, or flush, and we have to flush an instruction if the branch resolution says that your prediction is wrong. So this is the guideline of drawing a pipeline diagram. So given this, right? Okay, Byron, question?
Yeah, so can you go back to the previous slide? I was kind of wondering, like, when you say like flush an instruction if the branch resolution says it's mispredicted, how do you know which registers to
Okay, so we will talk about that later, right? But here's the guideline, right? And right now, our processor doesn't have a branch predictor, so don't worry about this.
Okay.
Okay, so if we have a pipeline processor like this, right? So for the very first cycle, we know the PC, so we can advance to the next, so we can fetch the instruction. In the next cycle, because no one is doing instruction decode, so the added instruction can be instruction decode. And because the first instruction is not a branch instruction, so we can fetch the next instruction since it's always PC plus 4. And for the third cycle, we can keep going because if you look at the execution stage, no one is using it. So add instruction can go in there. And when the add instruction go in there, it would free up the instruction decode stage for the low word. And the sub instruction can be fetched. And at this point, you can see like for the fourth instruction, well, so for the low word instruction and the add instruction, they are all operating on different registers. So there's no conflict, and because it's just read, so all the values are produced. And then for the next cycle, the add instruction goes to in its memory stage since no one is using that, and other instruction can advance 1 stage. And right now for the store word instruction, we can fetch it. And at this time, add instruction will put the result of register 1 into the register file. But at this point, store word instruction is not using that register. So we still have no trouble, no issue with that. And now in the next cycle, the store word instruction needs to read register 1, and the register 1 is already updated by the add through the last cycle, so we can keep going. So if you keep drawing this pipeline diagram, you will figure out for these pieces of a code, we have successfully achieved a CPI that is very close to 1. So if you think about like this, right? And if you look at this code, right? So if you have all instructions pipelined, so and in fact, every processor that we have right now is a pipeline processor. No matter how crappy your processor is a pipeline processor. So every process, well, except for those ones that you produce in CSE141. But other than those processors, all the commercialized processors, they are mostly pipeline. And given that, right? So MUL instruction is pipeline. Shift instruction is pipeline. So no matter what instruction is, every instruction is pipeline. So as long as you can keep your hardware resource busy, right? As long as you can keep filling your pipeline, the CPI of a certain instruction doesn't matter as long as your code is able to keep the pipeline busy, right? And for this case, it's especially the case since we can produce the result of I through a simple add. So the I won't be the critical bottleneck, and there are tons of stuff between the next multiplication and the current multiplication to do. So the multiplication is not even the critical path that will keep your pipeline underutilized. So here, so this explains why the left-hand side code is slightly better than the right-hand side code. Plus, the left-hand side code has fewer instructions to execute. So it gives you slightly better performance. And it's all because of, and the reason why multiplication is not an issue in performance because the pipeline parallelize the execution of all instructions and make the small difference in the CPI between the MLL instruction and the shift instruction becomes insignificant. All right. So before you leave the lecture, there are several things that I want to let you know. So first of all, you have a busy week next week. We have reading quiz due tomorrow, but next week, Monday, we have assignment 2. Wednesday, we have assignment 3, and there is midterm next Thursday. And make sure that you will be available during the lecture time next Thursday because we will be using Zoom to help people online. And the reason why we make the midterm available during that time because suppose if you pick the class and there shouldn't be any conflict in your schedule. So make sure that you are available at that time. And if you, I know a lot of you probably want to raise your hand right now regarding what the midterm is about, and everything about midterm will be announced in next Wednesday. So pay attention to that. And in the lecture on the next Wednesday, we'll also provide a review, a highlight, and a sample midterm. Other than that, I will see you later in the lab lecture or see you tomorrow.